How much do we truly understand about the giant planets of our solar system, and why is it that each time science believes it has reached an answer, the universe quietly opens doors to mysteries that are deeper, broader, and more elusive than ever before? In the cold darkness of deep space, a spacecraft once traveled in silence for 2 decades. It crossed more than 7 billion kilometers, journeying farther than any place humans have ever physically reached. NASA named this spacecraft Cassini, launching it in 1997 as part of one of the most ambitious missions ever undertaken by humanity. Cassini was more than metal, circuitry, and fuel. It became our eyes, our memory, and our collective longing to understand, carried gently into the cosmos. Throughout those long years, Cassini sent millions of images and streams of data back to Earth, revealing the breathtaking beauty of Saturn, its delicate rings seemingly drawn from light itself, and distant moon worlds hidden beneath layers of ancient ice. But in time, that journey had to come to an end. Cassini did not fade quietly into the emptiness of space. It chose its own ending, and even in its final moments, as its systems were pushed beyond their limits, Cassini continued to transmit data, as if unwilling to miss even the last breath of its mission. It was a decision grounded in science, yet guided by ethics, a silent affirmation that when humanity reaches outward to explore the universe, we are not only seeking knowledge, but also carrying the responsibility to preserve mysteries that do not yet belong to us. And in the moment Cassini vanished into Saturn, perhaps what remained was not only data, but a lasting sense that the universe is always larger than our understanding, and that humanity's journey of exploration, like a dream, never truly comes to an end. When we drift towards Saturn as we understand it today, we are never approaching the planet alone. We are moving along paths shaped by a long presence that stayed, circled, and returned again and again. Nearly everything we now sense about Saturn's rings, its atmosphere, its magnetic field, and its moons, comes through the steady companionship of the Cassini-Huygens mission. A journey that unfolded not in moments, but across decades of quiet observation. Cassini-Huygens was one of only a small number of spacecraft ever to reach Saturn, yet its influence quietly surpassed all others. Earlier, visitors passed through quickly, collecting brief impressions before continuing outward. Cassini remained. Over a span of roughly 20 years, including 13 years moving patiently within Saturn's orbit, it traveled a total distance measured in billions of kilometers, tracing looping paths that allowed gravity and time to reveal their pattern. During this long stay, it helped identify 6 previously unknown moons, subtle bodies woven into the planet's gravitational rhythm, and provided the foundation for thousands of scientific studies that continue to shape our understanding. What made Cassini invaluable was not the quantity of images alone, though many of them remain among the most striking ever returned from the outer solar system. Its deeper contribution came from continuity. Cassini gathered an unbroken stream of measurements, sensing changes in Saturn's gravity, listening to the structure of its magnetic field, following the motion of charged particles, and observing how rings and moons exchange energy over time. Instead of offering isolated snapshots, it revealed Saturn as a living system, one whose behavior only becomes visible when watched slowly, across many seasons. Through this steady presence, Saturn's rings were no longer seen as fixed decorations, but as records of motion and interaction. Subtle waves traced the influence of nearby moons. Gaps and edges reflected resonances, repeating with calm regularity. Cassini's instruments measured how mass shapes space around the planet, and how that shaping guides the movement of both ice and dust. Each orbit added depth, not by changing direction, but by allowing the same structures to be seen again, under new light and alignment. This long mission did not emerge suddenly. It grew naturally from earlier encounters that hinted at what remained unseen. When Pioneer 11 first reached Saturn near the end of the 20th century, it confirmed that Titan, the planet's largest moon, was wrapped in a dense atmosphere. That single fact lingered. An atmosphere suggests circulation, chemistry, and history unfolding slowly. Voyager spacecraft followed, expanding the view and refining measurements, yet their paths were already set, their instruments limited by the designs of an earlier era. They could not stay, and they could not descend. Cassini was conceived as the next calm step forward. It was designed to remain with Saturn and to carry a companion, the Huygens probe, built specifically to enter Titan's atmosphere. Launched in the late 1990 seconds, Cassini carried with it decades of accumulated curiosity, shaped by the understanding that some questions require not speed, but patience. It marked a transition from brief flybys to long-term companionship, from distant observation to sustained presence. Reaching Saturn required its own slow choreography. The Sun's gravity holds firmly to anything attempting to leave the inner solar system, and Cassini could not travel outward in a straight line. Instead, its path unfolded as a gentle weaving through planetary neighborhoods. It passed Venus twice, returned close to Earth for another carefully planned encounter, and then continued toward Jupiter, gathering a final assist before setting its course for Saturn. During one of these returns, Cassini passed remarkably close to Earth, at a distance comparable to that of many satellites quietly circling our planet. From this proximity, the precision of the journey becomes easier to sense. There was no drama in the passage, only accuracy, calculations made years in advance unfolding as expected. Each planetary flyby acted as a subtle exchange, a shared moment of gravity that adjusted Cassini's speed and direction without force or urgency. The journey itself became a reminder that movement through the solar system is always collective, shaped by many worlds acting together. As Cassini moved farther from the Sun, light grew faint, and a different challenge emerged. Solar panels could no longer provide enough energy. Cassini carried its own steady source of power, generated by the slow decay of radioactive material. This internal warmth functioned like a small, constant hearth, producing electricity reliably even in the deep cold near Saturn. It allowed instruments to remain active year after year, sensing fields and particles long after sunlight had weakened. This choice reflected careful planning rather than boldness. The power source was selected because it offered endurance, not excess. It supported Cassini quietly through its long life, making extended observation possible where no other option could. With energy secured, the mission's scientific goals could unfold without haste. Cassini's instruments were tuned to explore Saturn as an interconnected system. They traced the structure of the rings, measured the depth and motion of the atmosphere, mapped the magnetic field, and studied the many moons that move through this environment. Titan, in particular, stood out as a world of layered complexity, while smaller moons revealed how even modest bodies can shape rings and fields through resonance and gravity. Over time, Saturn became less a distant symbol and more a place shaped by gentle, persistent forces. Alongside this long orbital study, one carefully planned moment unfolded quietly. Attached to Cassini for most of the journey was Huygens, a compact probe built through international collaboration. For years, it remained inactive, protected, waiting. Once Cassini reached Saturn, Huygens was released and allowed to drift alone toward Titan, guided only by gravity and time. For weeks, it traveled in silence, carrying a simple internal timer set to awaken it shortly before entering the Moon's atmosphere. The descent that followed unfolded over several hours. Huygens passed through thick layers of haze, measuring pressure, temperature, wind, and chemical composition as it fell. Images sharpened gradually, revealing channels, planes, and rounded features shaped by flowing liquids. The probe had been designed with humility. Its primary task was to observe during descent, and its structure allowed it to survive landing, even to float briefly if it encountered liquid. When it finally touched the surface, on terrain resembling the dry bed of a former lake, the remaining data it returned were a quiet gift beyond its central purpose. Huygens fell silent as its limited power faded, exactly as planned. Yet, in that brief encounter, Titan became tangible. It emerged as a solid world with texture and history, shaped by processes that echo familiar patterns while remaining distinctly its own. This moment complemented Cassini's long vigil, extending the mission's reach beyond Saturn itself and into questions of chemistry and evolution that unfold slowly under distant light. As Cassini continued its long companionship with Saturn, there came a time when the nature of the journey began to shift, not toward urgency, but toward depth. Fuel, which had quietly enabled years of steady motion, was slowly diminishing. Yet even this limitation did not arrive as an ending. Instead, it opened a new phase of movement, one shaped by intention and care, where the remaining energy would be used to explore regions that had always been present, yet never visited so closely. For most of its life around Saturn, Cassini followed stable, well-understood paths, looping through space in a rhythm that balanced safety and observation. Then, gradually, those paths began to narrow. The spacecraft adjusted its course, rising high above the northern regions of the planet, before dipping back down toward the delicate threads of the rings. Each orbit carried it a little closer, allowing instruments to sense details that had previously remained just beyond reach. These motions were not sudden. They unfolded as a sequence of carefully repeated arcs, each one building gently upon the last. Over time, Cassini began to move through a region that feels almost unreal when imagined from afar. Between Saturn itself and the inner edge of its main rings lies a broad but delicate gap, shaped by gravity and motion, long hidden from direct exploration. Cassini passed through this space again and again, not forcing its way through, but slipping between moving structures that had been circling the planet for ages. With each pass, the spacecraft gathered measurements of particles, fields, and faint material that drifts there, suspended between ring and planet. These final orbits carried a quiet philosophy. When extending the mission further would no longer reveal new perspectives, the remaining fuel was used to accept higher risk in exchange for deeper understanding. This was not a gamble in the usual sense. It was a deliberate choice to allow the last movements of the spacecraft to bring us closer than ever before, into regions where gravity, dust, and charged particles meet in subtle balance. Cassini's motion became a kind of slow aerial dance, precise and controlled, tracing narrow passages shaped by Saturn's immense presence. As these orbits unfolded, another quiet decision framed everything that followed. Within its vast system are worlds like Titan and Enceladus, moons that show signs of internal oceans and complex chemistry. As Cassini's long companionship with Saturn entered its final phase, fuel slowly diminished, not as an abrupt ending, but as a natural narrowing of possibilities. The remaining energy was used to guide the spacecraft onto paths it had never traveled before, bringing it closer to Saturn than ever, into regions shaped by delicate balances of gravity, dust, and motion. So the plan was shaped with care. Cassini would enter Saturn itself, dissolving harmlessly into an atmosphere where nothing could survive long. This choice reflected a broader understanding that exploration carries responsibility, and that preserving the quiet integrity of distant worlds matters as much as observing them. In this way, the final movements of Cassini were guided not only by physics, but by restraint. During the grand finale orbits, Cassini also turned its attention to some of Saturn's smallest companions. Nestled within the rings are tiny moons, bodies so modest in size that they might easily be overlooked, yet their influence is unmistakable. Cassini passed close enough to reveal their shapes in detail. Some appeared smooth and gently sculpted, with broad ridges of material gathered around their equators. Instead of deep scars from impacts, their surfaces looked softened, as if continually reshaped by the slow fall of icy dust. These moons act quietly within the rings, guiding material as they move. Their gravity gathers and redistributes particles, maintaining narrow gaps and sharp edges. Over time, dust from the rings settles onto them, building rounded forms that seem almost improbable, like small objects molded by the environment itself. Through Cassini's close observations, the rings began to feel less like a single structure and more like a living system, one that includes even the smallest participants. Beyond individual moons, Cassini revealed patterns woven through the rings themselves. In the broad expanse of the B ring, faint spiral waves could be traced, subtle variations in density that wrap around Saturn many times. These waves are not static marks, they are the result of gravitational rhythms, especially the gentle interactions between moons whose orbits shift over long periods. As these moons move, they leave signatures behind, written into the rings as repeating patterns. Seen this way, the rings become a kind of record, not of sudden events, but of ongoing motion. The spacing of the waves reflects cycles that repeat over years, quietly encoding changes in orbital relationships. Information from decades earlier still lingers in these patterns, preserved by the slow circulation of countless icy particles. Cassini did not need to disturb the rings to read this history. It only needed to watch closely enough, long enough, for the story to reveal itself. In other regions, Cassini observed features that look almost playful in their shape. Elongated disturbances stretch through the rings, resembling the outline of a fan or a pair of wings. These structures are created by tiny embedded bodies, too small to clear a full gap, yet large enough to influence the particles around them. As they move, material piles up ahead and trails behind, forming temporary patterns that slowly change and fade. These small bodies are not permanent architects. They gather material for a time, then lose it again through gentle collisions and drifting motion. Their presence shows that even within the rings, processes of gathering and dispersal continue quietly. Matter is never fully still. It circulates, clumps briefly, then spreads again, guided by gravity and motion rather than force. As Cassini's orbits brought it closer to Saturn itself, the view shifted from rings to clouds. Near the boundary between day and night, sunlight skimmed the atmosphere at a low angle, casting long shadows across towering cloud structures. These shadows reveal depth, showing that Saturn's atmosphere rises and falls in layers, shaped by internal heat and slow circulation. The planet's surface, though lacking a solid boundary, displayed texture and form through light alone. In some views, the dark side of Saturn was never fully dark. Faint light, reflected from the rings, reached into the night hemisphere, softly illuminating clouds from above. The planet and its rings were no longer separate elements, but parts of a single luminous system, each influencing how the other appears. Cassini captured these moments without urgency, allowing light and shadow to speak quietly of connection. Gradually, the time came for Cassini's final descent. On its last approach, the spacecraft entered the uppermost layers of Saturn's atmosphere at tremendous speed, moving faster than any storm or current below. Thin gases began to brush against its structure, and instruments sent back their last measurements, sampling particles, fields, and atmospheric composition directly for the first time. These data flowed continuously, carried by radio waves traveling outward, while Cassini moved inward. The spacecraft used its remaining energy to keep its antenna pointed steadily toward Earth, maintaining connection as long as possible. As atmospheric resistance increased, control became harder to maintain. Motion grew less stable, forces rose, and the environment quickly exceeded what the spacecraft was built to endure. Within moments, Cassini's long journey dissolved into heat and motion, becoming part of Saturn itself. There was no sharp boundary between observation and disappearance. Data simply continued until it did not. What remained was a unique record of Saturn's upper atmosphere, gathered in the only way possible, through direct passage. This final act added depth to everything that came before, completing the picture of a planet observed from afar and, at last, from within. And even after the signal faded, the influence of Cassini did not end. Its measurements continue to move through our understanding. Much like the rings continue their slow turning around Saturn, the paths traced during the grand finale remain present as ideas and patterns, while the planet itself carries on, unchanged by the brief touch, holding its clouds, its rings, and its quiet rhythms in the dark. These were not mysteries that demanded resolution, but patterns that invited patience. They revealed a world where motion and stillness coexist, where enormous structures can remain steady for years, and where even something as basic as the length of a day refuses to settle into a single number. Near Saturn's North Pole, Cassini observed one of the most striking atmospheric structures in the solar system. A vast hexagon encircles the pole, wide enough that each of its 6 sides could span a planet like Earth. At its center lies a deep polar vortex with an eye reminiscent of a hurricane, while around it, clouds are swept along by winds that move at extraordinary speeds. Yet the hexagon itself holds its shape. It does not drift freely with the surrounding atmosphere. Instead, it remains locked in place, rotating in step with Saturn's deep interior. This stability gives the impression of a rigid frame embedded within flowing gas. Clouds slide beneath its edges, seasons change, and sunlight alters the colors of the polar region. Yet the 6-sided outline persists. Over the years, Cassini watched the polar region transition from winter darkness into sunlight, revealing subtle shifts in hue and contrast. Through it all, the hexagon remained, suggesting a connection between surface weather and motions occurring far below the visible clouds. The hexagon hints that Saturn's atmosphere is shaped not only by winds and storms, but by deeper rhythms tied to the planet's rotation. And yet, when scientists tried to measure that rotation directly, they encountered an unexpected difficulty. For rocky planets, a day can be timed by watching surface features turn. For gas giants, other signals must be used. One common method relies on magnetic fields, which are usually tilted relative to a planet's spin axis. As the planet turns, this tilt produces a repeating signal, a natural clock. Saturn, however, does not cooperate. Its magnetic axis is almost perfectly aligned with its axis of rotation. This near alignment means that the usual magnetic clock barely ticks at all. Cassini measured radio emissions associated with Saturn's magnetosphere, emissions that Voyager had once used to estimate the planet's day. But over Cassini's long stay, this signal refused to stay fixed. The apparent length of a day drifted slowly, sometimes becoming slightly longer, sometimes slightly shorter, changing by about 1% over time. Instead of a steady rhythm, Saturn offered something closer to a wavering signal. The planet's internal rotation continued. Yet the radio emissions reaching space were shaped by processes higher up, in the ionosphere and magnetosphere. These regions are influenced by charged particles, electric currents, and winds that move independently of the deeper interior. The result is a clock whose hands bend and flex, making it unreliable as a measure of the core's true motion. This confusion deepened when Cassini examined Saturn's energy balance. The planet emits significantly more energy than it receives from the Sunday. Some of this excess comes from slow gravitational contraction, a gentle release of heat left over from formation. But Cassini's data suggested additional complexity. The upper atmosphere was warmer than expected, especially near the poles. Auroras appeared and shifted even when the solar wind was relatively calm, implying that internal processes were contributing to their brightness. In this picture, Saturn appears to glow from within. Charged particles, some originating from the rings and moons, spiral along magnetic field lines and rain down near the poles, heating the upper atmosphere. Deeper inside, immense pressures compress hydrogen into exotic states, releasing heat through friction and phase changes. These internal energy flows drive strong winds and electrical currents in the upper layers, currents capable of distorting the magnetic environment that Cassini measured from afar. When these charged winds move through conductive regions of the atmosphere, they interact with the magnetic field itself. The field is still generated deep inside by a dynamo process. But what Cassini sensed was the field after it had passed through layers of moving, electrically active gas and plasma. It is as if the true magnetic signal were filtered through a shifting medium, emerging altered by the journey. One way to imagine this is to think of a rotating magnet hidden behind a thick, conductive veil. The magnet turns steadily, but the veil carries its own currents and motions, bending the field lines before they escape into space. To a distant observer, the signal appears smooth, nearly symmetrical, and subtly variable, masking the precise motion that lies beneath. Saturn's deep rotation remains present, but it is partially concealed by the planet's own complexity. Faced with this ambiguity, attention turned to a different kind of record. Saturn's rings, long admired for their beauty, became tools of measurement. The planet's gravity is not perfectly uniform. Tiny asymmetries, linked to internal structure and rotation, tug on the rings in specific ways. These tugs generate waves at certain distances, patterns that can be measured with great precision. The rings respond to Saturn's gravity much like a calm surface responds to distant vibrations. Subtle disturbances ripple outward, forming wave patterns whose spacing and shape encode information about their source. By carefully analyzing these waves, scientists could infer the rhythm of Saturn's interior, much as seismologists infer Earth's interior from distant tremors. From this approach emerged a new estimate of Saturn's day, one that differed by several minutes from values derived from radio signals. This measurement did not rely on magnetism or radiation, but on gravity itself, recorded quietly in the motion of countless icy particles. What once seemed like decoration became a sensitive instrument, revealing a fundamental property of the planet through gentle oscillation. This realization reframes how we see Saturn. The rings are not merely orbiting debris. They are responsive, dynamic structures, constantly shaped by forces both visible and hidden. They register the planet's internal motions over time, preserving information in patterns that change slowly, if at all. In this way, Saturn's most iconic feature becomes a bridge between what we see and what lies unseen. Even as these insights settle, they do not close the story. Cassini's data continue to be examined, yielding new connections long after the spacecraft itself dissolved into Saturn's atmosphere. Future missions, such as a rotorcraft designed to explore Titan's surface and skies, will add new chapters to this system's unfolding narrative. Each mission builds upon the quiet foundation Cassini left behind. There are hints, too, that Saturn itself is changing. Evidence suggests that the rings may be relatively young on cosmic timescales, and that material from them is slowly drifting into the planet. If so, the bright rings we see today may be temporary, a passing phase in a much longer history. Far in the future, Saturn could appear very different, its outlines softened by time. For now, Saturn remains as Cassini knew it, a planet of layered motion and subtle concealment. Storms can hold their shape for years. Magnetic signals drift without settling. Rings whisper the rhythm of the interior. None of these behaviors rush toward resolution. They simply continue, offering patterns to anyone willing to watch long enough, while Saturn turns beneath its clouds, keeping time in a way that does not need to be fully named. As our attention drifts outward from Saturn, another presence begins to shape the wider architecture of the solar system. Jupiter does not announce itself through delicacy or subtlety. Its influence is felt through mass, through gravity, and through long-term balance. It is the largest of the planets, a body so substantial that its motion gently reshapes the paths of others, including the Sun itself. To understand Jupiter is not to focus on surface detail at first, but to sense weight, position, and the slow consequences of having so much matter gathered in one place. Jupiter moves around the Sun at a distance several times farther than Earth's path, beyond the orbit of Mars, and just outside the broad region where the asteroid belt resides. From this position, it completes one journey around the Sun in a little under 12 Earth years. Even from this distance, it appears bright in our night sky, its size allowing it to reflect sunlight generously. When compared to Earth, the scale difference becomes immediately apparent. Jupiter's diameter is more than 10 times larger, and its volume is so vast that many Earths could fit inside. Its mass exceeds that of Earth by hundreds of times, making it the dominant planetary body in the system. Because of this mass, Jupiter serves as a reference point. When we speak of large planets, Jupiter becomes the comparison by default. It defines what a gas giant is within our own system. Its composition, dominated by hydrogen and helium, reflects conditions present during the earliest stages of planetary formation. In many ways, Jupiter resembles a fragment of what the Sun itself might have been had it not grown large enough to ignite. The influence of Jupiter does not stop at its own orbit. Its mass is so significant that the Sun does not sit perfectly still as Jupiter moves. Instead, both bodies circle a shared balance point, known as the barycenter. This point lies not at the Sun's center, but slightly beyond its surface. The result is a slow, subtle motion of the Sun itself, a gentle response to Jupiter's pull. From a distance, the system appears as a quiet dance, with Jupiter leading a rhythm that even the Sun follows. This shared motion highlights an important truth. Jupiter is not simply a passenger orbiting a central star. It is an active participant in shaping the solar system's dynamics. Its gravity extends far beyond its cloud tops, influencing the paths of planets, asteroids, and comets over immense spans of time. In this sense, Jupiter acts as a secondary anchor, helping define the structure of the system as a whole. Closer to the planet, gravity reveals itself in more immediate ways. Near Jupiter's cloud layers, the pull is more than twice what we experience on Earth. Objects moving nearby feel this force strongly, their paths bending as they pass. Over the solar system's history, this immense attraction has altered countless trajectories. Some bodies were drawn inward and captured as moons, forming one of the richest satellite systems we know. Others were stretched, fragmented, or redirected, never becoming planets in their own right. During the early stages of planetary formation, Jupiter's presence reshaped the environment around it. In the region between Mars and Jupiter, material that might have coalesced into another planet was instead stirred and scattered. The result is the asteroid belt, a population of fragments held in a delicate balance by Jupiter's gravitational influence. Rather than allowing quiet assembly, Jupiter's gravity introduced motion and disruption, preventing large-scale growth while preserving countless smaller bodies. This same influence extends inward, subtly affecting the long-term stability of planetary orbits. Over extremely long timescales, Jupiter's gravity contributes to small changes in the paths of even the innermost planets. These effects unfold so slowly that they feel almost abstract, reminders that stability in the solar system is dynamic rather than fixed. Everything moves, adjusts, and responds, guided by mass and distance rather than intention. Yet Jupiter's gravity is not only a force of disruption. From another perspective, it acts as a filter. Many objects arriving from the distant reaches of the solar system encounter Jupiter first. As they pass, its gravity can alter their paths dramatically. Some are drawn into new orbits, some are sent outward again, and some are absorbed by Jupiter itself. In doing so, Jupiter reduces the number of wandering bodies that continue inward toward the smaller, more fragile planets. This role has often been described as protective, though it is best understood as a natural consequence of mass. Jupiter does not choose what it deflects or captures. It simply exists, and its gravity does the rest. Over long periods, this has contributed to a calmer inner system than might otherwise exist. Earth and its neighboring planets occupy a region shaped, in part, by Jupiter's steady presence farther out. Occasionally, Jupiter's interactions with incoming objects leave visible traces. Brief markings can appear in its cloud tops, subtle darkened regions that fade with time. These moments pass without lasting disturbance, absorbed into the planet's vast, restless atmosphere. They serve as quiet reminders of Jupiter's role as an intermediary between the inner system and the distant outskirts beyond. Taken together, these influences present Jupiter as more than a single planet. It becomes a structural element of the solar system, a massive organizer whose gravity participates in nearly every long-term motion. Its presence helped determine where planets could form, how debris is distributed, and how stable certain regions remain over billions of years. And yet, despite all this power, Jupiter's influence unfolds gently. Nothing happens all at once. Orbits shift slowly, paths bend gradually, effects accumulate across timescales that dwarf human experience. Jupiter's role is written not in sudden change, but in patient repetition. In gravity applied continuously and without pause. As Jupiter continues its wide, steady circuit around the Sun, it carries this influence forward. The inner planets follow their familiar paths. The asteroid belt maintains its delicate balance. Comets arrive and depart. All of it unfolds within a framework shaped by Jupiter's mass, quietly and persistently. From a distance, Jupiter appears serene, wrapped in bands of cloud and light. Beneath that appearance lies a gravitational presence that anchors much of the solar system's long-term order. It does not guard through action, but through being, holding its place in space, allowing everything else to move in response. Even from far beyond Earth's orbit, it shines with steady brilliance, outshining nearly everything around it. Its light is strong enough to cast faint shadows, a quiet reminder that size and reflectivity matter as much as distance. For many people, Jupiter becomes the first planet they truly notice, easy to find, patient in its motion, and generous in what it reveals. Through even modest telescopes, Jupiter offers detail. Broad bands stretch across its face and small points of light. Its largest moons line up beside it like attentive witnesses. What professionals study with spacecraft and instruments, observers at home glimpse in simpler form. The same planet serves both curiosity and careful measurement, creating a gentle continuity between wonder and understanding. Those bands are Jupiter's most recognizable feature. They wrap fully around the planet, arranged in alternating light and dark zones that follow lines of latitude. The upper cloud layer is relatively thin, yet within it, motion never truly stops. The clouds are composed largely of frozen ammonia crystals, suspended in powerful winds that move at different speeds depending on latitude. Deeper down, other materials rise slowly upward, carried by convection, bringing trace compounds into sunlight. As these materials reach higher altitudes, they are altered by solar radiation. Subtle chemical changes produce the colors we see, from pale creams to deeper browns and rust tones. These coloring agents are not fixed paints, but products of ongoing processes. Over months and years, bands can fade, darken, narrow, or widen, while still maintaining their overall structure. Jupiter's atmosphere behaves like a living canvas, continuously refreshed, never fully redrawn. Within and between these bands, storms form. Some are brief, appearing and fading over weeks. Others persist far longer, gathering energy from the planet's rapid rotation and deep internal heat. Among them, one feature has held attention for centuries. The Great Red Spot is a vast, swirling storm, large enough to envelop a world like Earth, turning steadily against the flow of surrounding clouds. This storm has been observed since the early days of telescopic astronomy. Over time, it has changed. Its size has slowly decreased, and its color has shifted through shades of red, orange, and even pale tones. Yet it remains present, a long-lived vortex maintained by Jupiter's immense atmospheric energy. Its altitude is slightly higher than nearby clouds, allowing it to interact more strongly with sunlight, which may help shape its distinctive hue. Nearby, other large storms have formed and endured. Some have merged, others have drifted apart. One smaller, red-tinted storm emerged from the combination of several vortices and continues to circulate today, quieter than its famous neighbor but still persistent. Together, these storms show that Jupiter's atmosphere can store and sustain motion for astonishing lengths of time, far beyond what is possible on smaller planets like Earth. The reason for this endurance lies deeper than the clouds themselves. Jupiter is composed primarily of hydrogen and helium, the same elements that dominate stars. As pressure increases with depth, hydrogen transitions through different states, from gas to liquid, and eventually into a form that conducts electricity. This metallic hydrogen region occupies a vast volume inside the planet and plays a central role in its behavior. Jupiter spins rapidly, completing a rotation in about 10 hours. This swift rotation stretches the planet slightly at the equator and enhances the organization of atmospheric bands. The interior rotation does not proceed uniformly. Different layers move at different speeds, creating shear that feeds storms and helps maintain their structure. The planet's internal heat, left over from formation and slowly released, adds further energy to the system. Because of its composition, Jupiter is sometimes described as a star that never fully ignited. It contains abundant hydrogen, yet it lacks the mass required to trigger sustained nuclear fusion. Instead of shining by fusion, it glows faintly with heat generated by compression and slow contraction. This places Jupiter in an intriguing position, partway along a spectrum that runs from planets to stars, shaped more by mass than by category. One consequence of metallic hydrogen deep inside Jupiter is an extraordinarily powerful magnetic field. As electrically conducting material moves within the planet, it generates a vast magnetosphere that extends far into space. This magnetic environment is immense, larger than the Sun itself if visualized in certain ways, and it interacts continuously with charged particles from both the planet and its surroundings. Jupiter does possess a ring system, though it is far subtler than Saturn's. Its rings are faint and composed mainly of fine dust, supplied by small inner moons whose surfaces are slowly eroded by impacts. These rings are difficult to see from afar, yet they form part of a broader environment shaped by gravity and magnetism working together. Within Jupiter's magnetosphere, conditions vary dramatically. The large Galilean moons orbit within this magnetic domain, shielded from the solar wind, but immersed in streams of energetic particles. Some regions are relatively calm, while others are intense, shaped by interactions between the magnetic field and material ejected from moons like Io. This environment is dynamic and complex, a space filled not with emptiness, but with motion and invisible structure. All of these elements combine to create the Jupiter we recognize. Bright bands reflect sunlight, storms circle endlessly. Deep within, hydrogen flows under pressure, generating magnetism that reaches far beyond the clouds. None of this operates in isolation. Each layer influences the others, forming a planet defined by interaction rather than simplicity. As we remain with Jupiter, there is no need to single out one feature as more important than the rest. The Great Red Spot does not dominate through force, but through persistence. The bands do not impress through sharp contrast, but through continuity. Jupiter's story is one of sustained motion, energy recycled rather than expended, patterns maintained over time. And so Jupiter continues, rotating beneath its clouds, storms turning slowly, magnetic fields stretching outward, rings whispering faintly around it. Seen from afar or up close, it remains a world where scale invites calm rather than urgency, offering an image of vast processes unfolding steadily, without pause, under a distant Sunday. Far beyond the familiar brightness of Jupiter and Saturn, another giant planet moves in near silence. Uranus follows a distant path around the Sun, so far away that sunlight arrives softened and pale, spreading gently across its atmosphere. One full orbit takes many decades, and from this remote position, Uranus often feels like a world set apart. Quiet, faint, and easy to overlook. Even its name marks a subtle difference, drawn from Greek tradition rather than Roman, hinting at a planet that does not quite fit the usual pattern. From its distant orbit, Uranus traces a slow circle that lasts most of a human lifetime. Years pass on Earth while Uranus advances only slightly along its path. This remoteness shapes everything about the planet, from its low temperatures to its subdued appearance. Yet distance alone does not explain why Uranus feels so unusual. Its most defining trait is not how far it is from the Sun, but how it turns as it moves. Unlike most planets, Uranus rotates with its axis tipped almost entirely onto its side. Instead of spinning upright like a top, it rolls along its orbit, presenting first one pole, then the other, toward the Sunday. This extreme tilt creates seasons unlike any others in the solar system. For long stretches of time, one hemisphere remains bathed in continuous sunlight, while the opposite hemisphere lies in prolonged darkness. These conditions persist not for days or months, but for decades. During these extended seasons, the Sun traces a slow circle near the horizon of the illuminated pole, never setting. On the dark side, night holds just as steadily, with no sunrise to mark the passing of time. Only during brief periods near equinox does Uranus experience something closer to a familiar day-night cycle. And even then, the Sun stays low, skimming the horizon rather than climbing high into the sky. This arrangement reshapes how energy is distributed across the planet. Instead of gentle seasonal shifts, Uranus endures extremes of illumination and shadow. Heat accumulates slowly and dissipates just as slowly. Atmospheric circulation responds not to daily heating, but to long-term imbalances, creating patterns that unfold over many years. The concept of a season here is less about weather and more about orientation, about which half of the planet is allowed to face the sun at all. In size, Uranus remains unmistakably a giant. Its diameter is several times that of Earth, and its volume is vast. Yet when mass is considered, the picture changes. Uranus contains far less material than the gas giants closer in. Its mass, while substantial, is spread through a large volume, resulting in surface gravity slightly gentler than Earth's. If one could stand upon a hypothetical surface within the clouds, the pull would feel familiar rather than overwhelming. This balance between size and mass reflects Uranus's true nature. It is not built primarily from dense rock, nor is it dominated by deep, thick layers of hydrogen like Jupiter. Instead, Uranus belongs to a different category, often called an ice giant. Here, the word ice does not mean frozen solid in the everyday sense, but refers to compounds such as water, ammonia, and methane, compressed and heated into unusual states under immense pressure. Beneath Uranus's thin outer atmosphere lies a vast interior region rich in these materials. Temperatures rise quickly with depth, reaching levels where substances we think of as ice behave more like hot, dense fluids. This mantle forms the bulk of the planet, surrounding a small rocky core and supporting the layers above. The atmosphere itself is only a thin veil by comparison, composed mainly of hydrogen and helium, with a small but important contribution from methane. Methane plays a key role in shaping Uranus's appearance. It absorbs red light from the sun, allowing blue and green wavelengths to dominate what is reflected back into space. The result is the planet's calm blue-green color, smooth and subdued compared to the banded drama of Jupiter. This color remains relatively uniform, reinforcing the impression of a quiet, reserved world, even though complex processes continue beneath the surface. Within the deep mantle, pressure and heat create conditions unlike anything on Earth. Models suggest that methane molecules may break apart under these extremes, releasing carbon. That carbon, squeezed by immense pressure, could form solid diamond. Over time, countless tiny diamonds might fall slowly through the mantle, drifting downward like a silent rain, accumulating in layers far below the visible atmosphere. This idea of diamond rain remains theoretical, yet it offers a gentle way to imagine the inner life of Uranus. Instead of violent motion, there is slow transformation. Carbon reorganizes itself, matter changes phase, and heat moves outward over long timescales. Whether diamonds truly fall or not, the interior of Uranus clearly hosts chemistry and physics that differ fundamentally from those of rocky planets and gas giants alike. These deep layers may also explain another unusual feature of Uranus. Its magnetic field is not aligned neatly with its rotation axis, nor is it centered on the planet's core. Instead, it is tilted and offset, creating a magnetosphere that behaves in unexpected ways. As Uranus rotates, its magnetic field sweeps through space with an irregular rhythm, shaped by the conductive materials moving within the mantle rather than by a symmetrical core. The extreme axial tilt adds another layer of complexity. As Uranus rolls along its orbit, the orientation of its magnetic field relative to the Sun changes dramatically over the course of a year. This leads to magnetospheric dynamics that evolve slowly, responding to seasons measured in decades rather than days. The space around Uranus becomes a place of shifting boundaries, where charged particles follow paths that are anything but simple. Despite these complexities, Uranus presents itself with restraint. Its ring system is narrow and dark, difficult to detect from afar. Its moons are modest in size, quiet companions rather than dominant features. There are no vast storms like Jupiter's Great Red Spot, no towering ring structures like Saturn's. Instead, Uranus invites attention through difference rather than display. In this way, Uranus challenges familiar expectations. A planet can be large without being overwhelming, cold without being inert, distant without being simple. Its sideways rotation redefines seasons. Its interior blurs the line between solid, liquid, and gas. Its magnetic field refuses symmetry, Each of these traits stands alone, yet together they form a coherent whole. A planet shaped by balance rather than excess. As we remain with Uranus a little longer, its quiet differences begin to multiply. What first appeared as a tilted, distant planet gradually reveals a surrounding system that feels just as unconventional. Rings that absorb light rather than reflect it, moons that drift in delicate and sometimes unstable arrangements, and a magnetic field that seems unwilling to line up with anything familiar. Around Uranus, symmetry is rare, and order often arrives in unexpected forms. Encircling the planet is a system of rings that could hardly be more different from Saturn's. Instead of broad, bright bands, Uranus is surrounded by narrow, dark rings that seem to hide rather than announce their presence. They are so dim that they reflect less light than wet soil on Earth, making them difficult to see unless conditions are just right. These rings were not discovered through images at first, but through absence, when the light of a distant star flickered as Uranus passed in front of it, revealing thin, sharp interruptions. Later observations confirmed that Uranus possesses many such rings, most only a few kilometers wide, tracing precise paths around the planet. Additional faint rings were found farther out, extending the system more than expected. Their darkness suggests a composition rich in water ice, mixed with organic material altered by radiation, surfaces that have been processed and darkened over time. Rather than pristine relics from the planet's birth, these rings appear relatively young, likely formed from collisions or breakups that occurred long after Uranus itself settled into place. Seen this way, the rings resemble scars rather than ornaments. They mark events, moments when moons may have shattered or reassembled, leaving behind debris confined by gravity into narrow paths. The system feels active, even if change unfolds slowly, reminding us that Uranus has not been frozen in time since its formation. Just inside and among these rings moves a collection of small moons. Uranus has many satellites, but the inner group plays a special role. These bodies orbit close to the planet, interacting directly with the rings through gravity. One of them, larger than the rest, was captured in detail by a passing spacecraft decades ago, revealing an irregular surface shaped by impacts and time. These inner moons do not follow perfectly stable paths. Their orbits gently tug on one another, shifting over long periods. Simulations suggest that some may eventually collide or merge, while others could break apart, contributing fresh material to the rings. In this region, moons and rings form a connected system, matter cycling between solid bodies and fine debris, reshaped again and again without hurry. Farther out, Uranus is accompanied by a set of larger moons, each with its own quiet character. Miranda, Ariel, Umbriel, Titania, and Oberon form the main family. They are cold worlds, dominated by ice mixed with rock. Their surfaces marked by craters, ridges, and fractures. Some display signs of past internal activity, as if heat once stirred beneath their frozen exteriors. Among them, Miranda stands out with its patchwork terrain, where cliffs, valleys, and mismatched regions lie side by side, suggesting a complex history. Others appear more uniform, yet still bear traces of stress and movement. Beneath their surfaces, models allow for layered structures, with rocky cores surrounded by icy mantles. In some cases, pressure and residual heat may have been sufficient to sustain liquid water for a time, hidden deep below. These possibilities echo themes seen elsewhere in the solar system. Around different giant planets, icy moons repeatedly emerge as places where water may persist beneath solid shells. Uranus's moons extend this pattern outward, showing that potential environments for liquid water are not confined to one region or one type of planetary system. Even here, far from the Sun, complexity finds room to exist. Beyond these major moons lies another population, smaller and more distant. These irregular satellites follow tilted, elongated orbits, some even moving in directions opposite to Uranus's rotation. Their paths suggest that they did not form alongside the planet, but were captured later, drawn in by gravity during a time when the outer solar system was more crowded and chaotic. These moons behave like long-term visitors, circling far from the planet, preserving clues about interactions with distant regions such as the Kuiper Belt. They speak quietly of encounters and exchanges that shaped Uranus's surroundings, leaving behind a mixed family of companions with different origins. All of this motion unfolds within a magnetic environment unlike any other. Uranus possesses a magnetic field comparable in strength to Earth's, yet its geometry is strikingly different. The field is tilted sharply relative to the planet's rotation axis and offset from the center by a significant amount. Instead of emerging symmetrically, it appears displaced, as though generated from a region not aligned with the core. As Uranus rotates, this tilted magnetic field sweeps through space in an unusual pattern. The magnetosphere does not form a simple, steady bubble. Instead, it rolls and twists, responding to both the planet's rotation and its sideways orientation relative to the Sunday. The result is a magnetic tail that stretches far behind the planet, wound into a spiral shape, like a coiled spring slowly unspooling into space. This structure changes with the seasons. Because Uranus lies on its side, the angle between its magnetic field and the incoming solar wind shifts dramatically over the course of its long year. At times, the magnetosphere faces the sun directly. At other times, it lies almost sideways, forcing charged particles to follow complex paths. The space around Uranus becomes a place of constantly changing geometry, where magnetic boundaries drift and reshape themselves over years. These magnetic peculiarities point back to the planet's interior. Rather than being generated in a compact, central core, Uranus's field may arise from conductive layers within its deep mantle, where water, ammonia, and other compounds exist in hot, pressurized states. Movement within these layers, offset from the planet's center, could naturally produce a field that is both tilted and displaced. In this way, Uranus links its internal structure to its external environment. The same unusual interior that allows for exotic states of matter may also drive a magnetic field that defies symmetry. The rings, moons, and surrounding space all respond to this field, experiencing radiation and particle flows shaped by its irregular motion. Taken together, the Uranian system feels balanced in an unconventional way. Nothing aligns neatly, yet everything continues to move in long-term harmony. Rings persist despite their fragility. Moons follow paths that evolve but endure. Magnetic fields twist without breaking. The planet does not simplify itself for observation, and it does not need to. As Uranus continues its slow journey around the Sun, its dark rings trace narrow lines in space, its moons maintain their quiet companionship, and its magnetic field stretches and coils far beyond the planet itself. Change arrives gradually, measured in decades and centuries, not moments. In this distant realm, complexity does not shout, it unfolds softly, inviting observation without demanding resolution. While Uranus rolls onward, carrying its tilted world through the cold light of the outer solar system. At the far edge of the solar system, where sunlight arrives weakened and time stretches almost beyond familiar meaning, Neptune moves along its quiet path. It is the last of the giant planets, so distant that its light takes hours to reach us, and so slow in its orbit that a single year there spans more than a century on Earth. Yet despite this remoteness, Neptune is anything but still. It is a place of motion, of powerful winds and shifting storms, a world where activity persists even under the faintest warmth of the Sunday. Neptune entered human awareness not through a telescope, but through mathematics. Long before it was seen, its presence was felt indirectly, written into small irregularities in the motion of Uranus. Careful calculations revealed that something unseen must be exerting a pull from farther out. When astronomers finally turned their instruments to the predicted location, Neptune appeared almost exactly where the equations suggested. In this way, Neptune became a quiet testament to the reach of celestial mechanics. A planet discovered first on paper, then confirmed by light. Its distance is immense. Neptune orbits roughly 30 times farther from the Sun than Earth does, so far away that even the largest telescopes struggle to resolve details from the ground. From this range, the planet appears small and faint, a blue point against the dark. One full orbit around the Sun takes about 165 Earth years. Since its discovery, humanity has not yet witnessed Neptune complete a single journey along its path. Time there unfolds on a scale that resists human intuition. For more than a century, Neptune remained largely mysterious. Only in the late 20th century did a spacecraft pass close enough to transform it from an abstract idea into a tangible world. When Voyager 2 flew past Neptune, a single visit changed everything. What had been a blurred disk became a dynamic planet with rings, moons, clouds, and storms. In a brief encounter, Neptune revealed complexity that no Earth-based observation could fully capture. Voyager's images showed bands and bright clouds moving rapidly across the planet, along with large, dark storms embedded in the atmosphere. It confirmed that Neptune possesses a ring system, faint and fragmented, and it discovered several moons previously unknown. In that short passage, Neptune emerged not as a quiet, frozen remnant, but as an active world shaped by powerful forces. Like Earth and Mars, Neptune's axis is tilted at a moderate angle. This gives the planet recognizable seasons, though each one lasts decades rather than months. As Neptune moves slowly along its orbit, sunlight shifts gradually from one hemisphere to the other. These seasonal changes are subtle but real. Over time, they alter how heat and gases are distributed through the atmosphere. Even at this distance, the Sun still matters. Though its light is far weaker than at Earth, small changes in illumination can affect Neptune's appearance. Observations over recent decades have shown variations in brightness, particularly in one hemisphere. As temperatures rise slightly during seasonal change, methane that had been frozen out of the upper atmosphere can rise again, modifying cloud structure and reflectivity. The result is a planet that responds gently but perceptibly to the passing of its long seasons. What makes Neptune stand apart, however, is the speed of its atmosphere. Despite receiving less sunlight than Uranus, Neptune hosts the fastest winds ever measured on a planet in the solar system. Near the equator, winds race around the planet at astonishing speeds, in some regions approaching or exceeding 2,000 kilometers per hour. Some of these winds even blow opposite to the direction of the planet's rotation, a reminder that atmospheric circulation follows its own rules. Within this restless flow, large storms appear and disappear. Voyager observed a massive dark vortex, comparable in size to Earth, drifting through Neptune's atmosphere. This great dark spot was a dominant feature during the flyby. Yet, when astronomers looked again years later, it was gone. In its place, new dark spots had formed elsewhere, only to fade again over time. These storms behave differently from Jupiter's Great Red Spot. They do not persist for centuries. Instead, they seem temporary, lasting years or decades before dissolving back into the surrounding flow. Neptune's atmosphere feels more transient, its structures less anchored, shaped by forces that favor change rather than permanence. The presence of such intense winds and shifting storms raises a quiet question. How does a planet so far from the Sun maintain such energetic weather? The answer appears to lie beneath the clouds. Neptune radiates more energy into space than it receives from sunlight. Internal heat rises from within, supplying the atmosphere with a steady source of power. This sets Neptune apart from Uranus, which emits very little internal heat. Though the two planets are similar in size and composition, their thermal histories seem to have diverged. Neptune retains warmth from its formation or from processes deep inside, while Uranus appears comparatively subdued. This internal energy on Neptune fuels convection, strengthens winds, and supports the rapid formation and decay of storms. The contrast between the two ice giants suggests that their paths were shaped by different events. Subtle differences in formation, or ancient collisions, may have determined how much internal heat each planet retained. Whatever the cause, the result is clear in their present behavior. Neptune remains active and expressive, while Uranus responds more slowly to the same distant Sunday. Beneath Neptune's atmosphere lies an interior much like that of Uranus, dominated by water, ammonia, and methane, compressed into hot, dense states. These materials conduct heat upward, feeding the dynamic weather above. Deep within, pressure may also break apart methane, allowing carbon to reorganize into new forms, though such processes unfold far beyond direct observation. All of this motion occurs in near darkness, guided by faint sunlight and persistent internal warmth. Neptune's storms come and go without announcement. Its winds surge continuously, tracing paths that never settle for long. The planet does not present a single, enduring landmark, but a sequence of changing patterns. As Neptune continues its slow journey around the Sun, it carries this restless atmosphere with it. Seasons shift over decades. Storms form, fade, and are replaced. Winds race endlessly around the planet, driven by heat from within rather than light from without. In this distant realm, activity does not depend on closeness to the Sun, but on what a planet holds inside, quietly releasing energy over time. Inside Neptune, matter exists in unfamiliar states. Around it, rings and moons follow paths shaped by capture, imbalance, and long memory. Nothing about this system feels entirely settled, yet everything continues with quiet consistency. Beneath Neptune's blue atmosphere lies an interior that closely resembles that of Uranus. The outer layers are thin, composed mostly of hydrogen and helium, lightly tinted by methane that filters sunlight into cooler hues. Below this atmospheric veil stretches a vast mantle, rich in water, ammonia, and methane, compressed and heated into what scientists describe as hot ice. This is not ice as we know it, but dense, fluid material held under immense pressure, warm enough to flow and conduct electricity. Deeper still, a rocky core anchors the planet, surrounded by this ocean-like mantle. At the boundary between these layers, pressure reaches extremes far beyond anything achievable on Earth. Under such conditions, familiar molecules are forced into new arrangements. Methane may break apart, releasing carbon that is squeezed into solid form. In this environment, carbon could crystallize as diamond, forming tiny grains that drift slowly downward through the mantle. This idea of diamond rain remains a hypothesis, yet it provides a gentle image for processes that are otherwise difficult to imagine. Instead of dramatic upheaval, Neptune's interior may be shaped by continuous transformation, matter changing phase and density as it moves through layers of pressure and heat. Compared to Uranus, Neptune appears to retain more internal warmth, allowing these processes to remain active, feeding energy upward into the atmosphere above. This internal structure helps explain Neptune's magnetic field, which, like Uranus's, defies simple geometry. Rather than aligning neatly with the planet's rotation axis, Neptune's magnetic field is strongly tilted and offset from the center. It does not emerge symmetrically, nor does it trace a simple loop through space. Instead, it reflects motion within the conductive mantle, where electrically charged fluids circulate in complex patterns. As a result, Neptune's magnetosphere behaves in an unusual way. Auroral activity exists, but it is faint and elusive, often appearing away from the poles rather than concentrated there. Much of it belongs to a subtle class of emissions that require sensitive instruments to detect. These auroras trace regions where charged particles drift and settle gently rather than crashing in dramatic displays. The weak solar wind at Neptune's distance contributes little energy, leaving internal processes to shape what light does appear. This magnetic environment mirrors the planet's broader character. Nothing is entirely absent, yet nothing is overstated. Fields are present, but uneven. Emissions occur but remain quiet. Neptune's magnetosphere stretches outward, interacting with space in ways that are still being unraveled, guided more by internal motion than by external forcing. Encircling the planet is a ring system that continues this theme of irregularity. Neptune's rings are faint and dark, difficult to observe even with powerful instruments. 5 main rings trace narrow paths around the planet, composed of fine particles that absorb more light than they reflect. Among them, one ring stands out not for its brightness as a whole, but for its unevenness. Within this outer ring, material gathers into localized arcs, compact regions where particles cluster instead of spreading evenly. These arcs have persisted for decades, defying expectations that such concentrations should disperse quickly. Their continued presence suggests subtle gravitational influences, likely tied to nearby moons whose resonances help confine material to specific locations. In this way, Neptune's rings differ from those of Saturn. They do not present broad, continuous records of motion, but fragmented signatures, where history is written in segments rather than lines. The rings feel provisional, held together by balance rather than abundance, offering hints rather than full explanations. Beyond the rings, Neptune's family of moons comes into view. 14 are currently known, most of them small and distant. Among these companions, one dominates the system almost entirely. Triton is unlike any other moon in the outer solar system. It is large, cold, and remarkably complex, carrying more mass than all of Neptune's other moons combined. Triton follows a path that immediately sets it apart. It orbits Neptune in the opposite direction of the planet's rotation, and its orbit is inclined, not aligned with the planet's equator. These traits strongly suggest that Triton did not form alongside Neptune. Instead, it was likely captured, drawn in from the distant population of icy bodies beyond the planet. In many ways, Triton resembles Pluto and other objects from the Kuiper belt. It has a thin atmosphere, composed mostly of nitrogen, and its surface shows signs of active geology despite the cold. Geyser-like plumes have been observed, rising gently and settling back down, driven by seasonal heating and volatile ices. Clouds drift above its surface, faint and transient, hinting at cycles that respond slowly to distant sunlight. This captured origin reshaped Neptune's system. As Triton settled into its backward orbit, its gravity likely disrupted any original moons, scattering some, destroying others, and contributing material to the ring system we see today. Triton's presence tells a story of interaction and rearrangement, where capture leads not to stillness, but to long-term transformation. Other moons orbit farther out, quieter and more irregular. Proteus, the second largest moon, remains oddly shaped despite its size, marked by deep craters that speak of past impacts. Its form suggests that it never fully relaxed into a sphere, preserving the imprint of collisions that occurred long ago. Even larger bodies can carry such memory when conditions allow. At the fringes of Neptune's influence, small moons trace wide, elongated paths, taking decades to complete a single orbit. These distant satellites define the outer boundary of the system, moving slowly through space, where Neptune's gravity still holds sway. Their existence shows how far the planet's reach extends, even at the edge of the solar system. Taken together, Neptune's rings and moons form a system shaped by capture, imbalance, and endurance. Nothing here feels accidental, yet little feels symmetrical. Each component reflects a history of interaction, where objects arrived, settled, and adapted to new gravitational realities. As this journey through the giant planets draws gently to a pause, Neptune offers a fitting final presence. Its interior hides extreme states of matter. Its magnetic field refuses alignment. Its rings gather in fragments. Its largest moon moves against the flow, carrying the signature of distant origins. These are not details often emphasized in simple descriptions, yet they define the planet's true character. Neptune does not resolve its complexities for us. It allows them to coexist. Processes continue beneath the clouds. Rings persist in narrow arcs. Triton circles steadily in reverse. Far from the sun, under dim light, Neptune remains active in its own restrained way, holding together a system that feels both complete and unfinished, inviting quiet reflection rather than conclusion, while it continues its long path through the outer dark. Now we turn our attention to the quiet gap between Saturn and its rings, and drift in to see what truly lives in that seemingly empty space. Between the cloud tops of Saturn and the inner edge of its rings, there is a narrow space that looks empty at first glance. From far away, it seems like a simple border, a thin, dark band where brightness drops before it rises again in the rings. Yet as we drift closer with our attention, we begin to notice that this quiet gap is not truly empty. It is a place where dust, light, magnetic fields, and gravity all cross paths in a very delicate way. We can imagine ourselves following Cassini as it slipped into this space during its final orbits. For most of its long journey, the spacecraft stayed outside the rings or just skimming their edges, careful and distant. Then, near the end, its path was reshaped into a series of plunging loops that threaded the needle between Saturn and the innermost ring material. It is as if, after years of watching from the balcony, we step down and walk across the stage itself, brushing past the curtain that separates planet from ring. From here, Saturn fills most of our view. The upper clouds, banded and softly lit, curve away beneath us with a slow, massive grace. Above and around us, the rings arch overhead as a vast, pale bridge. In this gap between them, the light feels different. There is less of the sharp scattering from ring particles and more of a gentle glow reflected from both planet and rings, mixing and softening in the thin haze. You might picture it as standing in a high, quiet corridor where light comes in from two sides at once. Even in this place, which looks like pure darkness, when viewed from far away, there is matter drifting. Fine grains of dust, fragments of ice no larger than smoke particles, glide past at enormous speeds. Plasma, a faint gas of charged particles, threads its way through the region, guided by invisible magnetic field lines that connect planet and rings. To our eyes, this space would still look almost completely empty. To a sensitive instrument, though, it is full of whispers. Cassini carried ears for those whispers. As it moved through the gap, its instruments listened to the clicks and hisses of charged particles, the faint electrical crackle where ring material and Saturn's magnetic field meet. We can let ourselves imagine that sound as a softened, distant static, like a radio tuned between stations. For our purposes tonight, it is not important to distinguish plasma waves from radio emissions or energetic particles. It is enough to know that the gap is alive with a subtle kind of weather that our bodies cannot feel, but our instruments can trace. Every time the spacecraft passed through this corridor, it traced a slightly different path. The ring plane was sometimes above it, sometimes below. Sometimes Cassini approached the planet from the sunlit side, sometimes from the side turned toward night. Each orbit added another layer of detail. The density of dust was measured again and again. The strength and shape of the magnetic field were mapped more finely. The tiny variations in gravity, caused by how mass is distributed inside Saturn, tugged on the spacecraft just enough that those tugs could be measured. Over time, these repeated crossings built up a more complete picture of what lies beneath the clouds. As we float here in imagination, we can think of the gap as a kind of transition zone, a boundary that is not really a line but a volume. Above us, ring particles orbit in nearly perfect circles, colliding gently, exchanging momentum, slowly evolving over long stretches of time. Below us, the atmosphere churns, with jets and storms and deep flows that may extend thousands of kilometers downward. In between, we have this slender space in which neither world fully dominates. Gravity from the planet pulls inward. The structure of the rings pulls outward. Through the shared dance of particles and resonances, magnetic fields thread through everything, tying the system together the way unseen strings hold a mobile in balance. For many years, there was a question about how much material actually fell from the rings into Saturn. Were the rings almost eternal, slowly changing but essentially stable? Or were they in the process of being erased, their matter raining down over geologic time? The orbits through the gap helped answer that question. Cassini could directly measure how much ring material was crossing this space and entering the upper atmosphere. That rain is gentle on human timescales, but steady on Saturn's. Grain by grain, molecule by molecule, the rings and the planet are exchanging matter in this thin, invisible stream. You might picture very fine snow falling through a twilight sky. The flakes are so small that they almost do not register as separate objects. They only become visible when you shine a beam of light through them. In a similar way, the dust and icy particles passing through this region show themselves most clearly when illuminated by the spacecraft's measurements. To us, resting and listening, it is enough to feel that even in the most apparently empty spaces of a planetary system, there is a quiet traffic of matter moving steadily, according to the patient rules of gravity and time. There is another layer of quiet meaning in this gap. It is the space Cassini had to pass through in order to come to a peaceful end. The decision to send the spacecraft into Saturn's atmosphere was shaped by care for the moons. Worlds like Enceladus and Titan, with their subsurface oceans and complex chemistry, are considered possible homes for life. To keep them pristine for any future probes, Cassini could not be left drifting in a long, uncontrolled orbit that might one day bring it crashing down onto an icy surface. Instead, its path was designed to thread this narrow corridor repeatedly, gathering precious data, and then finally curve inward until the atmosphere itself embraced it. We do not need to dwell on that moment as a dramatic fall. For our purposes here, we can think of it as a return. A small, human-made object that had spent years in the space between worlds was guided into the planet that had been its constant companion. As it dipped into thicker and thicker air, the same instruments that had once tasted the ring gap sampled the upper atmosphere directly, sending back information until the friction became too strong and the signal faded. It is a gentle image, a long glide into a deepening golden cloud deck, data flowing outward like a final stream of thoughts. If we let our awareness drift away from the spacecraft and back into the gap itself, we find that nothing has ended here. Saturn still turns. The rings still orbit. Dust still sifts across this corridor, and invisible currents still carry charged particles along looping paths. The gap remains a place of passage, even without a visitor from Earth moving through it. This can be a comforting thought as we rest, that the universe holds many such spaces, slim and overlooked, where delicate exchanges are taking place all the time. You and I are not moving at tens of kilometers per second, and we are not threaded between a gas giant and a ring system tonight. Yet the idea of this gap can live quietly in our minds. It can remind us that what looks empty at a distance may be rich in structure when we take the time to pass through slowly and listen. It can invite us to notice the thin spaces in our own experience, the intervals between busy moments, the soft transitions at the edges of days, the small pauses where nothing obvious seems to happen. In those pauses, as in the space between Saturn and its rings, there can be gentle currents at work, rebalancing, redistributing, slowly reshaping the patterns around us. As we stay here a little longer, we can let the image of that narrow corridor remain with us. The planet below, the rings above, the stream of dust and light and fields flowing through in silence. The spacecraft has moved on, but the gap keeps its slow, continuous rhythm, and we are free to drift alongside it for as long as we wish. There is a soft paradox at the heart of Saturn. This is a world made almost entirely of gas and liquid, a globe of clouds and deep, flowing layers. And yet near its north pole we find something that looks solid, a hexagon. From above, the polar region hosts a six-sided pattern, a vast, rotating ring of clouds with straight edges and clean corners. It is as if someone had traced a geometric shape onto the top of a storm. Year after year, as Saturn turns and seasons slowly change, the hexagon persists, turning with the planet like a frame that never quite breaks apart. We can imagine ourselves drifting high above that pole now. The planet below is banded and soft, creams and golds and faint blues blending into one another. Then, closer to the top, a darker belt emerges, bending into a six-cornered path around a deep, whirling eye at the center. Nothing here is made of rock or ice. Every line is drawn in, moving gas. Yet the pattern holds. It is a reminder that even in a restless atmosphere, waves and currents can organize themselves into something that feels almost like a fixed structure. That sense of something steady inside something fluid runs through the whole story of Saturn and time. On a solid world like Earth, saying how long a day lasts is simple. We watch how long it takes for the ground beneath us to complete one turn with respect to the sun or the distant stars, and we can track that spin by following mountains, continents, or any fixed point on the surface. On Saturn, there is no hard crust we can see. The clouds we look at from space slide over one another at different speeds. Near the equator, they race. Closer to the poles, they may drift more slowly. If we tried to define a day by following the clouds, our answer would change depending on which band we watched. So, for a world like this, we turn to invisible structures, magnetic fields, and radio waves. Deep inside, beneath the clouds, Saturn is generating a magnetic field, a bubble of influence that shapes the motion of charged particles, guides streams of plasma, and produces radio emissions as those particles spiral along its lines. On another giant planet, such as Jupiter, the magnetic field is tilted relative to the axis of rotation. As the planet spins, the field sweeps around like a lighthouse beam, and the rhythms of its radio emissions give us a clear, repeating signal. That signal can be used as a kind of clock, a steady tap, tap, tap that marks each full turn. Saturn refuses to be that simple. Its magnetic axis is almost perfectly aligned with its spin axis. The beam does not swing dramatically through space, and the radio pulse is not as sharply defined. Over the years, as Voyager and then Cassini listened to those emissions, something even more curious appeared. The length of the radio day seemed to drift. Measurements taken decades apart did not agree exactly. The signal was sometimes a little faster, sometimes a little slower, shifting by about 1%. It was as if the ticking of a clock were wandering, not because the planet's deep rotation had really changed, but because the environment producing the radio waves was being gently pushed and pulled by other forces. To picture this, we might imagine a wind chime hanging from a quiet porch. The metal tubes will ring with a pitch set by their size and shape, but the pattern of their ringing depends on the breeze. Strong gusts make them sound often and loudly. A calm day lets them fall almost silent. The chime has its own character, but what we hear at any moment reflects the air around it. Saturn's radio emissions, shaped by its magnetosphere and the streams of plasma that fill it, behave in a similar way. They are influenced by the slow, breathing motions of charged particles, by the way sunlight and the solar wind interact with the planet's extended atmosphere. The radio clock tells a story that mixes Saturn's internal rotation with the variable music of its outer environment. If one clock is this uncertain, we look for another. And here, Saturn offers something unique: its rings. These wide, bright bands of ice and dust do more than scatter sunlight in beautiful ways. They also respond to the planet's gravity with great sensitivity. The pull of Saturn is not perfectly smooth. It is shaped by how mass is distributed deep inside, by the core, by the layers of metallic hydrogen, by the flows of material that may be moving around within. Those internal motions can set up waves that travel outward, just as movements within Earth cause tremors that travel through rock. In Saturn's case, some of these deep vibrations leak into the rings as faint, spiral ripples. If we imagine the rings as a wide, flat lake made of ice particles instead of water, then Saturn's interior becomes the distant shore where stones are being dropped. Each stone, each pattern of internal oscillation sends out a particular set of ripples. Far from the source, on the lake's surface, the pattern can still be detected if we look carefully enough. In the real Saturn system, those ripples show up as density waves, places where ring particles bunch together into narrow, brighter lines, separated by regions where they are more spread out. When Cassini looked at the rings with its instruments, and when scientists later examined high-resolution images and stellar occultations, they found fine patterns of such waves, repeating at regular intervals. Those intervals are not random. They are tied to specific frequencies of vibration inside the planet. By reading the spacing and shape of the waves, we can learn about how Saturn's gravity field is changing in space and time. That, in turn, gives clues about how fast its deep interior is rotating, and whether different layers are slipping past one another. In this way, the rings act as a kind of natural seismograph. They record, in their graceful curves, the internal rhythms of the world they encircle. Where the radio clock is flexible, buffeted by conditions in the magnetosphere, the gravitational clock encoded in the rings is quieter and more stable. It responds directly to how mass is arranged and moving under the clouds. It is slower to change. We might think of these as two different measures of the same underlying day, one written in the shifting language of plasma and light, the other in the more patient language of gravity and ice. There is something soothing about this image of two clocks. One ticks with a lively, variable beat, sensitive to every change in the space weather around Saturn. The other marks time with the nearly inaudible movement of billions of icy grains, each tiny collision and adjustment contributing to the long-term pattern. Between them lies the truth of how Saturn spins, not as a single rigid object, but as a layered, living system. If we drift our attention downward now, from the rings and their waves toward the planet's upper atmosphere, we find another sign that Saturn's timekeeping does not depend solely on the Sunday. The planet shines with more energy than it receives from starlight alone. Deep inside, it is slowly contracting and rearranging itself. Helium may be separating out from hydrogen and falling inward like a gentle rain of droplets, releasing heat as it sinks. This extra warmth rises, adding to the motions of the atmosphere, feeding long-lived storms and broad jets. At the poles, that internal energy and the magnetic field together give rise to auroras, curtains and ovals of light that circle the high latitudes. Sometimes these displays respond clearly to changes in the solar wind, brightening when a stream of charged particles from the sun sweeps past. At other times, they glow even when the solar wind is quiet, driven more by processes within Saturn's own magnetosphere. It is another reminder that the planet carries its own rhythms, not just the ones imposed from outside. We can let all of this settle into a single gentle idea. Saturn keeps time in more than one way. It turns beneath its clouds in a continuous, fluid spin that we can never see directly. Its magnetosphere sings in radio tones that speed up and slow down with the shifting state of charged particles. Its rings ripple with patterns that quietly encode the frequencies of deep interior motions. Its auroras flicker and flow at the poles, responding both to outer influences and to energy rising from within. No single number for the length of a day can capture all of these layers perfectly. As we rest with this thought, there may be a small comfort in knowing that not all cycles have to be nailed down to the second to be real. Saturn continues to rotate, whether we assign its day a precise count of hours or not. The hexagon at the pole keeps turning. The rings keep circling. The waves on that icy lake keep carrying messages from the inner regions to the outer edge. Very slowly, over years and decades, you might feel, in your own life, the difference between external clocks and inner ones. There is the time marked by alarms, by schedules, by the changing light outside your window. And then there is another kind of time, sensed more quietly in your body and mind. The slow adjustment after a long day, the way thoughts gradually settle, the pace at which you naturally drift toward rest. They do not always match exactly, just as Saturn's radio clock and ring clock do not always agree. Yet together they form a more complete picture of how your days unfold. If you like, you can let Saturn's layered timekeeping be a soft image to carry with you deeper into the night. Picture the planet turning steadily, the hexagon circling at the pole, auroral ovals breathing in gentle light, and far above, the rings responding to every subtle variation in gravity with almost imperceptible waves. Each part is moving according to rules that are both firm and forgiving. Each contributes its own measure of the day. We do not need to choose which measure is correct before we can appreciate the whole. We can simply acknowledge that some rhythms are meant to be known with precision, and others are meant to be felt. Just as the exact length of Saturn's day can remain slightly uncertain, and yet the world keeps spinning, so our own sense of time can soften at the edges without anything important being lost. As our attention drifts outward again, away from the details of fields and waves and internal heat, we are left with a calm scene, a pale, banded sphere, a faint hexagon at its crown, a thin halo of rings encircling it, marked by subtle ripples too fine to see from here. The planet turns. The rings whisper their faint responses, and the universe around them continues in its own vast silence. Time flows on, with or without numbers, and we are free, for now, to simply float alongside that motion, carried gently by its unhurried pace. As this journey slowly draws to a close, we can quietly look back on what we have just traveled through, not as a sequence of dry scientific facts, but as a long story of human curiosity, patience, and humility before the vastness of the universe. From giant planets shaped by relentless storms to delicate rings that are both fragile and ancient, to spacecraft missions that endured for decades, everything points toward a single, gentle truth. The universe is always larger than we imagine, and our understanding is only a small light carried into the deep night. Missions like Cassini did not carry instruments and fuel alone. They carried humanity's questions, our longing to know what hides behind thick clouds, within invisible magnetic fields, and inside motions so subtle they escape the naked eye. And even when such missions end in fire and atmosphere, their journey does not truly stop. It continues within data still being studied, within discoveries yet to unfold, and within the imagination of those who listen and wonder. Perhaps what matters most is not how many mysteries we have solved, but how each answer gently opens the door to many more questions. The universe does not rush to reveal everything. Instead, it invites us to learn how to wait, to observe, and to accept that some truths will remain beyond our reach for a very long time. It is this incompleteness that gives the journey of exploration its quiet beauty and lasting meaning. If you have stayed with us until these final moments, allow yourself to slow down just a little more. Take a deep breath. Feel the stillness around you, like the vast spaces that lie between the stars. In that stillness, knowledge no longer feels like something to hold on to, but like a calm reassurance that we are living within a universe that is both immense and gentle at the same time. Thank you for listening, for giving your time and your attention to this journey. Your presence is what transforms these cosmic stories into something shared, something felt. And this is not the end. Ahead of us remain countless surprises yet unnamed, countless secrets still hidden within the shadows between planets and distant stars.